Hello, my name is Anthony Hairston, and this is my presentation over representing nth-dimensional shapes using matrices. To start off, a lot of linear algebra goes into producing computer graphics. This application involves simulating and creating both realistic and unrealistic objects in such a way that they abide by their own sets of physical laws in various spaces. Furthermore, such applications of linear algebra and computer graphics are used in activities such as computer-aided design or CAD, video games, computer-generated imagery or CGI in movies and shows, augmented and virtual reality, and physics calculations. The movement of multiple objects in virtual space is normally achieved through the use of the advanced manipulation of matrices containing elements of the object being moved. This manipulation of matrices can also be denoted as matrix transformation, which can move the vertices of a shape by combining matrices with others to achieve a specified movement. Here we have just a few 3D transformation matrices. As you can see here, we have a rotation matrices for each of the axes on the 3D graph. If we want to scale up an object on a 3D graph, then we can use the scaling matrix, which can be used to either decrease or increase the size of an object. These three shear matrices manipulate the object in such a way that it becomes slanted, or much like a parallelogram if you're using a cube or a square. My application of some of these matrices included building a program that produced matrices that housed the points for various shapes. For example, when using the IN3 library in C++, I produced some shapes represented by the matrices as seen below. I built a 2x4 matrix representing the second dimension and 4 vertices or vectors that holds data for a square, as well as a similar format for a cube represented by a 3x8 matrix. Looking closer at the matrix representing the square, my program involved the use of binary numbers to produce a base 1x1 unit square in a virtual space. The matrix representing a cube uses the same method by column to produce a 1x1x1 unit cube that can be further manipulated by other transformation matrices. Before taking a dive into fourth dimensional objects, it is important to understand two basic characteristics of this dimension. The first is that just as a 3D object casts a 2D shadow when light is shined upon it, a 4D object would cast a 3D shadow when light is shined upon it. And the second is that the 3D shadow of a 4D cube is called a tesseract. The matrix transformation to reduce this shape will be seen in the following slides. To begin the creation of a tesseract, a cube with a specified size must be created. As seen to the left, the size is used as an eigenvalue to increase or decrease the cube shape matrix. The smaller cube is then produced by utilizing either a scaling matrix or eigenvalue to scale down the larger cube. Finally, the smaller cube is positioned to the same center as the larger cube by adding the value of the larger cube's size divided by 4. The final tesseract could be seen here with the final equation for achieving the inner cube. Here is some of the code that I used to produce the tesseract. Here where the arrow is pointing, a binary number is constructed for each column of the matrix to produce the best shape. The size of the larger cube is scaled down by the eigenvalue here, and the creation of the inner cube is done below with the help of the scaling and positioning matrices. Since the tesseract presented itself as a combination of two of the same objects, an array including the large and inner cube was utilized. A similar process was used for the square that can be seen here as a 2D matrix is created and subsequently populated. The matrix is then multiplied by its eigenvalue and pushed into the array. The same process was used for the cube, as a 3x8 matrix was created and subsequently populated using the binary numbers by column. It was also then multiplied by an eigenvalue and pushed into its own matrix. Here is the result of the code. This first matrix here represents the square and the subsequent points. So this point would be 0, 0 on a 2D axis or a 2D graph, 1, 0, 0, 1, 1, 1. And the same can be said for the cube, which is represented on the 3D axis or a 3-dimensional scale as seen here, in a 3x8 matrix, since the cube has 8 points. The tesseract becomes a little bit more complicated as both the big cube and the small cube need to be represented. Here we have another base cube of this size 1. And the small cube is a result of the transformation equation that we used earlier. These shapes can further be transformed by applying the other transformations, such as shear and various rotations. In conclusion, more advanced transformations based on user inputs are achieved through the use of graphics libraries such as OpenGL. Thank you for watching this video, and here are my references. Have a great day.